Hello, everybody, and welcome to this webinar. Thank you so much for giving us your time and joining us today. Before we get started with the content of the presentations, a few housekeeping notes. So just to let you know that this is being recorded, and tomorrow people who have registered for the webinar will receive by email a link to the presentation recording, so you can go back over this at your leisure and review things. There's also the option to get in touch with your sales contact at Mega, who will be able to help you out with inquiries or questions that you've got to follow up on this. So we invite you to do that, please, and we'll be delighted to help you with your queries. Also, while we're waiting a couple of minutes at the start of this hour, it's always good to give people time to catch up and jump from one meeting to another to log on and join us. Please also know that there's a Q&A section built into the app here, so that if you've got questions online while we're presenting, we'll do our best to try and keep up with them, but we may not be able to answer everything in real time. If we don't, we'll keep an eye on those and get back to you afterwards, or if I see quite a lot of repeated questions coming up, we'll answer them in a group fashion at the end of the session. We've left time for Q&A should it be needed. So with that in mind, and with the time just coming up to a couple of minutes past the hour, we'll start this properly. So welcome everyone. My name is Saul Matthews, and I am the Vice President of Sales at Synaptic. And as you'll see on the bottom left-hand corner of this first slide, Synaptic are powered by Mega, and Mega recently acquired a percentage of the company and is a major supporter of our technology. And indeed, this technology is available through the Mega network for condition monitoring purposes. So this is why you're seeing us talking to you here. And while I'm going to talk a little bit, I also want to introduce my colleague, Dr. Stephen Blair, who is our head of power systems and has a profound understanding of the technology and how it works. So we're going to kind of share the space here where I'm going to talk a little bit more commercially about business cases and how this technology helps people monitor and optimize operation of critical cable assets, whereas Stephen's going to go much more in depth on how this technology works and can be deployed. So with that, I'm going to move on a few slides, and I do invite people to ask Q&A as we go. This requires a little bit of explanation, so I'll start with a quick couple of slides on who we are. So Synaptic has been a company established for 10 years in Glasgow in the west of Scotland, where we invented a relatively new technology called distributed electrical sensing, or DES. Think of it as distributed sensors. This is completely passive sensing technology capable of monitoring critical parameters like voltage or current, where we can reach far outside of a substation, go very far away from it, over the fence, if you like, or somewhere very remote or inaccessible, so that we can measure and instrument critical medium or high voltage devices as if they were inside the substation. Our sensors require critically no power, so no control power or copper wiring, and they do not generate or receive any data. So there are no data networks or infrastructure required to get a measurement back to the center about a critical asset that might be otherwise very difficult to instrument. So if you hold in your minds the idea that there is this new ability to monitor and measure current and voltage completely passively without any critical infrastructure at the remote location, we hope to show you how this technology is used to either reduce the capital cost of instrumenting distributed energy systems and power networks, but also it has a direct operational benefit, because having visibility in real time of these assets, such as cable systems, gives you the ability to see problems coming and have enough time to plan effective interventions to avoid outage or to optimize scheduled maintenance. Now, you'll see some names on the slide here about who we are and customers that we work with as good examples from around the world in two main categories, so transmission and distribution or power utilities, as well as particularly offshore wind, who have significant problems in this domain. But if you think of the technology that you invented, this slide probably summarizes it best. Imagine that you've got effectively a very clever box centrally inside the substation firewall that's able to reach out and, as I said, jump over the fence and go far away to monitor something, for example, like underground cable systems, which is on the left-hand side of your screen, or maybe some remote circuits where you've got cable sections, or indeed subsea circuits, some of which can be extremely complex, such as offshore wind farms. And you can see we've color-coded this slide. The top half is in blue and the bottom half is in green. So this technology was designed for enhanced protection and control of complex circuits. And indeed, technology is certified independently as a kind of 5P class protection system. But today we want to talk to you about how this distributed sensor system is able to monitor cables which are underground or underwater, not to respond rapidly to a fault after it's happened, but to see these problems coming and help operations and maintenance teams do a better job of engaging with the asset and avoiding, or primarily avoiding these problems, and being able to access these locations at the right time for the right reasons. So that might sound like a lofty claim, but we'll take you through it now. And my colleague Stephen will take over from you as we talk about Greenlight, the technology product that we've invented to monitor cables. Stephen?
Okay, great. Thanks, Al. Yeah, so as Al said, I'll go through one of our products, which we call Greenlight, which is focused on this issue around condition monitoring of cables. So we see that the industry has a big challenge at the moment. Cables are resulting in a lot of outage time, and the resulting costs for operators can be quite significant, can be pretty eye-watering in some cases. And also a lot of these failures are happening in weak points, which are the joints and terminations of these cables, which conventionally are under-monitored at present. And we can see that failures for grid cables, which could be underground cables that are onshore, as well as offshore cables, can result in these significant losses primarily due to the loss of generation. So it's basically renewables simply cannot connect into the grid, and the owners of those generators don't get the revenue they expect due to this weak point in the cables. Offshore wind cable networks have a particular challenge because those cables are subsea, they're hard to get to, and the repair costs can be very significant. And we've also seen that the insurance claims that the offshore wind industry is claiming, the majority of that cost is coming from cable failures. So there's a clear financial incentive here, and we strongly believe that improved monitoring of these cables can find these issues early and avoid many of these instances, or at least mitigate the costs that are involved. So to give you a bit of background, in the UK, which is where we're based, there's a strong public body of evidence that's published by the regulator Ofgem. And here I'm quoting a few of these events that are specifically related to joints or terminations failing. And so some of these examples highlight the export cable for an offshore wind farm, but a significant portion of that cable is actually onshore in many cases. So it's just like any other grid cable and has a similar kind of topology and electrical parameters. So these costs will apply equally to onshore and offshore cables. So there's three main categories of costs here. There's the lost revenue due to the generation not being able to feed into the grid. There's the repair costs, which even for onshore can be quite significant, but it's exponentially more offshore. And also in the UK, we have this concept called OFTOs, the offshore transmission operators. They look after the export cables. They have a particular category of incentivization. So if there's any outage time of these cables, they are penalized for that financially. So, and again, these costs involved are all very high, looking at all of these examples. But the existing monitoring systems where they're installed are inadequate to actually find these problems, let alone give you early warning of these things happening. But in all of these 5 historical cases, Synaptic would be able to instrument these systems and our Greenlight product would be able to directly target these common failure modes, pretty much by being able to place the sensors very close to the joints and terminations. So that enables us to see things early and help optimize the maintenance activities and critically reduce the cost. So this slide shows how and where we find issues in cable systems. So failures in cables, as I said already, are commonly happening at joints and terminations, which are not adequately monitored by conventional monitoring systems, or those systems are simply too expensive to deploy at scale. So as Saul introduced earlier, we deploy passive point sensors that can measure phase current, screen currents, and temperature at these critical locations. That's not an exhaustive list, but that's typically what's applicable here. So for example, the bad weld event for the East Anglia 1 export cable, that led to a localized temperature increase at one of the joints onshore. So simply putting a temperature sensor there, and Synaptics temperature sensors they're very small and they're passive. They just need to be able to connect to a fiber. That would have seen the event emerge as it's happening, and allowing some options for mitigation. So for example, the power flow in that cable could have been restricted to, say, 80% of what it would normally be able to achieve, and that would prevent it from overheating, for example. And it at least keeps the system running before a repair can be scheduled. We can also measure screen currents at remote locations. That can unlock quite a lot of intel about what's going on and the health of the cable system in multiple different ways. Just to sort of zoom in a little bit on what that looks like, it's important to note that DTS and DAS are often kind of spec'd as the kind of standard approach for monitoring cables at the moment. And they do give you useful information about the cable integrity, but they tend to not give you any information about what's happening at the joints or terminations, because typically the fiber is routed around those locations. Whereas Synaptics' approach is to put the sensors at those weak points and see exactly what's going on. And we can place sensors as close as possible to these critical points. So that could include the screen bonding connection in joints. For terminations, it could be right at the termination where the cable conductor is bonded to the other conductor. Or it could be on a sheath voltage limiter, SVL, for example, in a link box. So these are all possibilities that we could readily deliver. And we're kind of filling that gap where DTS and DAS have a bit of a blind spot. We can complement that by filling this gap. So what is Greenlight? Well, it encompasses our full solution for cable condition monitoring. So that includes all of our sensor hardware, all of our kind of knowledge and expertise in building the physical sensors and the interrogation equipment. But it also includes layering on the data analytics, intelligent event alarms, and some visualization tools that can help operators see what's going on as early as possible. So that this includes insights into the cable health that were never really possible before, because we can reach far and wide and get and integrate lots of sensors together. So our objective of a Greenlight system is to operate in 3 different areas on slightly different timescales, which is covered in the next slide. So where we offer our kind of benefits is not just strictly condition monitoring. We're actually helping with other things. So we can help with accelerating the delivery or the installation and commissioning of the asset. It could be a wind farm, or it could be a grid-based cable. So basically, as soon as the joints and terminations or the cable is energized, we can start tracking what's going on and see if there are any initial anomalies, perhaps when there's still crews available to actually redo a termination or joint immediately. So that's one area we can help. The second area is about reducing the time to repair and improved availability of these assets. So basically finding signs of damage as early as possible and being able to track what's going on and give an early alarm for the operator to do something about in a way that suits them. So ideally, we want to find things very early before they fail, before it's a critical damage and before there's an outage. And we ideally give the operator time to schedule that repair and deal with it efficiently and cost effectively. And the third area is where we're trying to maximize the yield. So basically maximize the uptime of the circuit. And as well as the condition monitoring, which feeds into that, we're also offering a kind of enhanced real-time thermal rating, RTTR, which in addition to what's conventionally done with RTTR using DTS as the main input, we're also factoring in activity at terminations or joints, because sometimes they can be the bottleneck, and I'll come back to that later on. So for example, in the wind farm context, that allows operators to ramp up the power. Basically, typically converters will have some capability to ramp up by, say, 10% beyond the rating. But the operator can only do that if they're sure that the cables won't be damaged. So we provide that guarantee effectively. So this is what the Greenlight software dashboard looks like at the moment. So here we're seeing some data from a typical underground cable system. The data here, we've simulated it to make certain events happen, but it's based on a real cable in London that crosses the Thames. Behind the scenes, what Greenlight is doing is it's processing data from all of the sensors, and it's generating events at all different locations that are instrumented. And then we're applying some weightings to those events on these input factors to generate what we're calling a health score. And that score is calculated independently for every monitored joint and termination, as well as for the cable as a whole. So we aggregate that to show what each individual cable is doing. So the idea is that customers, operators, instead, they don't need to process a fire hose of data, or they don't get overwhelmed with excessive alarms. Instead, we're extracting what's useful and highlighting the locations that might need maintenance first. So we're doing basically an aggregation stage where we effectively pre-filter the data and recommend to the operator where those weak points, if they exist, where they are. Okay, so I'll now talk through some more specific examples of where we've applied this and some real data we've had from our previous deployments. So here we show an example of how a really simple metric, which is just derived from measurements of phase current and screen current, it can immediately highlight damage or an installation problem, such as, well, something at a joint that was perhaps either degraded, or maybe there was an initial installation problem that caused this issue. So it could be just, one of the steps in installing the joint was missed, and it had some impact later on in terms of the insulation quality or something similar. So simply by comparing phase current and screen current, or by looking at the ratio of those two numbers, we can immediately see if there's an anomaly, and that's what's shown here. So this is real data from a 400 kV cable in Europe, where we find that there was an anomaly in one location, and we're able to pinpoint exactly where that is, which joint or which phase of the cable was the kind of guilty one here. And we can also see that everything else that cable was doing is healthy and has a similar kind of linear behavior. So that means we can recommend to the operator, targeted maintenance of this joint on this phase would be a sensible thing, rather than the teams having to, walk down a very dark and unpleasant tunnel, and perhaps even dangerous tunnel, periodically to hope that they see things. So yeah, this gives the operator confidence in that when the cable's healthy, and also to intervene efficiently and cost effectively when something is spotted. So it's a kind of moving away from scheduled periodic inspections to targeted inspections that actually target the damage that's happened. I would also say that we didn't invent this technique. It's been available in the literature, in CGRE reports, and operators have used this, but they've used it using conventional technology. So that means a very limited duration of monitoring campaign, and they can only look at a relatively small section of the cable at a time. It's really challenging to do this by networking data, time synchronizing everything, and really understanding what's going on. But inherently, our sensor platform provides that synchronous data to make this possible. Okay, so the next example I want to talk about is we've conducted some testing of real termination, but this was done in a lab in collaboration with an operator. But we exposed this termination to high currents, to high temperatures, and also there were deliberate installation defects. So the contact rod inside the termination was had the wrong torque applied, so it effectively wasn't installed correctly. So, and that worked in the sense of it created a hotspot that developed in the termination, and our point temperature sensing was able to see it immediately. So that's the sort of knee point you can see on the plot here. This is because our sensor is placed directly on the termination as close as possible to that kind of contact point. Even temperature probes, like conventional sensors that were embedded in the conductor, couldn't see this. That's because they're just a little bit too far away from the termination, and they didn't see the hotspot develop. And that also goes for DTS fiber, which would similarly be too far away from the termination to spot this. And there's also the kind of the spatial resolution factor for DTS systems that mean it's not great at finding point temperatures because it's averaging things out. So this gives us good confidence that we're able to actually find these issues immediately and perhaps take action before the cable and the termination is stressed even more. So perhaps it could survive, enough time to efficiently and cost effectively, deploy a crew to go and repair this. We've also, just as an aside, we've also used the data from this experiment to estimate the conductor internal temperature, but from externally mounted sensors. So we've developed that transform of how to do that. So this kind of gives us the best of both worlds, particularly when we're looking at the rate of change of temperature and trying to judge if something critical has gone wrong in the cable or the termination. So we've got the combination of accurate point sensing at critical locations, and then we can infer the actual conductor thermal state internally as well. This a similar, well, in some ways similar. This is a different example, a completely different installation. So this is monitoring of an export cable for a real wind farm here in Scotland. And we had the benefit here of having access to our own data from our own monitoring system, where we're measuring phase current and temperature at terminations. But we were also able to get access to DTS data on the same cable. So what we found in this data is that synaptics sensing, about 20% of the year, our sensors were able to see that the termination was the hottest point in the system, whereas every other time of the year, somewhere along the length of the cable was the bottleneck. So what this means is that DTS alone, it gives you a decent impression of the thermal rating of that cable, but it's not tackling the thermal rating of the terminations at each end. So we're able to, again, fill that gap and provide a solution for RTTR, which is complete and gives you a full picture of what's going on. So in our Greenlight systems, by standard, we would actually include DTS in our offering. So again, we're getting the best of both worlds. We get the usual benefits from DTS, and its typical RTTR approach, but we can add in intelligence from our sensors. Simply by putting temperature sensors effectively at the termination, we can close off another gap and provide, basically a full RTTR system that's looking at the whole cable and all of the accessories. Yeah, so that's effectively an enhanced RTTR system that we have developed. Okay, so here's another interesting example. This is also from a 400 kV underground cable in a tunnel in Europe. And so we've seen the system actually go through a critical issue in real time when the entire tunnel actually flooded. So when that happens, we see the temperature drop rapidly, and we see that temperature drop. You can see on the top plot here that hits different parts of the cable at different times, and we're able basically to see how that flooding develops and affects the different joints get flooded at different times, and then also the phases, which are mounted at different heights in the tunnel, they get affected at slightly different times. So, and what happened in this case was the operator actually did a preventative step, and they disconnected the circuit on the 9th of March this year. And then on the 10th of March is when our sensors basically detected the flooding due to the drop in temperature. And then a couple of days later, actually the entire substation was flooded. So we lost the connection to our cloud data service. So that's basically when we lost data. So using this data, we've actually been able to refine what our Greenlight system is doing, the processing it's doing, so that when we see this data in the future, we can actually detect these events automatically. And it could be in a tunnel like this, or it could be a link box, out literally in a field in the middle of nowhere. If that gets flooded, then our temperature sensors can pick that up readily. Again, our temperature sensors are small, they're easy to install, and we can show if any location, effectively no matter how remote, if any location has been flooded at any time. Okay.
Stephen, do you mind if I just supplement that with a couple of points of explanation? Because while you've been speaking, I've been fielding quite a few questions from people that might require a little bit of explanation at this point. So hopefully you can all see on the left-hand side of this picture that kind of black circular device going around the screen there. So this is a conventional current transformer, and we use conventional industry standard current transformers or voltage transformers, and we attach our passive sensors to the secondaries, to the copper outputs from these devices. So that's why it's completely passive, right? We're using a standard primary transformer, but then how we're networking all of our sensors together makes for a very efficient system because it can reach so many remote or inaccessible locations. By comparison, if you wanted to instrument at a particular point along the cable here, maybe the temperature, you would physically attach a fiber all the way along it. And this is how distributed temperature sensing, or DTS, actually works. So it's using the fiber almost like a microphone to listen for changes along the fiber, which infer damage to the insulation. DTS, temperature sensing, infers maybe a hot spot where something's heating up and failing, or a cold spot because there's water ingress. And DAS, distributed acoustic sensing, by comparison, might be listening for and locating and characterizing impacts, maybe a third-party kind of intrusion, effectively. Someone drilling, for example, in the street and damaging a cable. But the point is this: distributed temperature sensing, DTS, and distributed acoustic sensing, DAS, are only monitoring the structural integrity of the cable itself. What we're trying to do is infer the health of the cable by understanding the electrical stresses that are going through the inside of the cable, and we're looking from the point of weakness, which are these joints and terminations. So these slides that we've been showing everyone for the last 3 slides here are real world examples of us instrumenting these cables and catching these events, in this case, a catastrophic flooding event. But previously, what you're seeing is the ability to get ahead of a problem and buy some precious time for the operations and maintenance teams to make informed decisions to plan an intervention and avoid a failure, because we're trying to give the earliest possible warning that we can see some kind of deviation from the others. And again, the benefit operationally is to say that you would only send people to a location to fix something because we have seen the problem, not because scheduled maintenance regimes are telling you this is the day to go and visit that location and check if it's okay. So if you can reduce the number of visits and you can better target and plan why you're going, where you're going, what you expect to fix there, you're going to save money and reduce operational cost, and in turn improve your availability and even yield by having more real-time information about how the asset is performing. So I hope that makes sense, and that should take care of quite a few questions that have come up in the meantime here, because maybe that wasn't made very specifically clear enough. So apologies for the interruption, Stephen, but I thought that might help.
Yeah, cool, thank you. All right, so I'll move on to the next point, really. So this diagram is mapping out the lifetime of a cable asset, including the joints and terminations, where, as we've said now, those tend to be where things go wrong. So there are various different stages of damage happening to the assets. Some causes can happen at manufacturing or during installation, which is a pretty common cause. And the damage can actually be induced or worsened by loading the asset, so actually just using it normally throughout its lifetime. Some sources of the damage can obviously be external, it could be weather, it could be animals or ship anchors, that sort of thing. But regardless of what caused it, Synaptic's approach is to find damage as early as possible in this process. So this means that the operator is able to intervene at early stages of the damage before the asset gets to critical failure. And we sort of said there are 2 categories here. There's hidden damage indicators, so things that are relatively subtle and difficult to find, but by our monitoring approach, by looking at, say, every joint, looking at the temperature or the screen currents in every joint, we can start to build a picture of what's normal in that asset, and we can readily generate alarms if something is drifting outside of that norm. And then there's the second category, which is more severe damage events, where things are actually starting to get pretty obvious that there's a failure. In terms of electrical stress, there could be, you could be seeing incipient faults, so there's an actual breakdown, although it's temporary. That indicates there's something wrong with the insulation at that location. On the thermal side, we could see hotspots start to emerge. And again, as I highlighted earlier, that allows us to intervene or allow the operator to intervene early before it actually, before something blows up and becomes an outage. That asset could be looked after in the meantime until a repair is possible. But however, although those more extreme, severe damage events are relatively easy to find, we still need our sensor platform to be able to put sensors at those remote locations. But still, we do focus on category 1, where we can find things as early as possible and give as much headroom for the operator to resolve it. There's also a point here on the kind of synergy with Megger, where Megger help at both the early stages of a cable's lifetime and when something goes wrong. So that could be, the usual kind of commissioning tests for a cable that are done offline, looking at partial discharge, looking at tan delta, for example. And then if something does go wrong, Megger are well established on locating faults and providing other information about the asset. So I just
may I add one thing on that one, Stephen? Sorry,
yeah,
just to help people think about this. So very often we'll find Obviously, best practice with mega test equipment during commissioning of a cable, that's vital. As Stephen alluded to earlier on, what tends to happen is that immediately thereafter, once you've energized the cable, if we are installed, you've got that instantaneous validation that all of those screen currents are correct and as planned, and you've got correct bondings and earthings, everything's working as expected while your contractor is even still on site. So that's the message about helping people, with more confidence in the commissioning process. But then there can often be an enormous period of time here. In fact, I was with a very large customer today on their site who are taking their cable offline and testing using all the correct best practices, and PD and TAN Delta or VLF, all the mega equipment is being used. But the period between tests by agreement with the regulator is 3 years. Now, in those 3 years, an awful lot of things can go wrong. An awful lot of problems can incur. And indeed, this customer has a significant problem with water ingress. The joint bays are flooding very gradually over time, and that could happen within a matter of weeks or a month. 3 years is just an awfully long time between testing. So what Synaptic technology is doing, and what Greenlight specifically is there to do, is to fill the gap between these static offline test events and see, well, what is that trend? Is it degrading as we planned, or is it worse than we planned, or are we actually doing better than we planned? And day to day, can we optimize the number of visits and inspections and checks that need to be undertaken to maintain that availability and high performance? And again, Stephen mentioned this, but if you do need to dynamically rate this cable and push it a bit harder sometimes for some certain reasons, that's really important, because you've got the ability to optimize that yield, that capacity, but safely without endangering the future longevity of the asset. So all of these day-to-day operational parameters become more visible and controllable between these enormous and expensive scheduled outage events, which typically for a high voltage cable could be anywhere from 5 to 10 days is typical. So very important to stress that we would love to always install Greenlight actually and design it in before the cable is even built, while it's being installed, and during commissioning, that we're ready to go as soon as it's energized. But because of the nature of the passive sensors that we use, you're able also to retrofit this system. So in the case of the customers that we've been talking to recently, this cable has already been installed for like 10 years, and the requirement is to see how long it will still be able to continue operationally despite some of these problems and these flooding events. And therefore, being able to retrofit this technology conveniently, safely, and fast is a major benefit. So I think when you think about all of those factors, the insurance of availability, the reduction or avoidance of major failure events, this has a big implication, not just yield, not even just availability and sort of safety concepts for grid operators, but also it's about the insurability and the fundamental reduction of risk in operating this asset, which otherwise you could argue is running on an assumption or a model of what should be happening. And what we're trying to do is make it much more empirical and deterministic. Is it okay? Should you intervene? Signposting problems so that the operator can make better informed decisions about whether to commit resources to fix a problem. So I hope that's clear from this diagram. There's a lot contained in this. And I'll stop myself there, Stephen, if you want to carry on. But I thought that was just, again, to address some questions that were coming up in the chat here.
Yep, great, cool. So I just wanted to quickly address the kind of how this works in comparison with partial discharge monitoring, because that is likely popped into the minds of people in the audience. So we try to categorize things here and show where Greenlight fits in. So there's offline testing, which it can include partial discharge monitoring and other things like TAN Delta to inspect the insulation quality effectively. So that, of course, has value. It's a very useful diagnostic tool. but it obviously requires the cable to be out of service so that signals can be injected at the appropriate levels, at the appropriate frequency to excite these events and see what happens. There is also a category of monitoring for partial discharge, which is done online. Obviously, this has some issues with the logistics required to actually install the equipment, because unlike Synaptics' approach, these sensors, they need local power supply, they need some kind of data networks, some approach to time synchronize things, most likely. So it becomes impractical to deploy this at scale. So typically it's done in a sparse way with relatively few installation locations, or it's done on a temporary basis. So it'll be like a kind of basically a handheld instrument that people would take during periodic maintenance campaigns. It does also suffer from the kind of some of the usual kind of gotchas with partial discharge monitoring. Often the data can be difficult to interpret. Typically, it requires an expert to tell you what's going on. Recently, we've seen some claims about some AI approaches to try and resolve that, but I think it still seems to be at least a couple of years away before that's reality. There is one operator at least is looking at the PD data only when there happens to be a transient on the cable. So it could be during a lightning strike or a switching transient, and that induces a high enough voltage where there's meaningful PD generated if there's some kind of defect in the system. So it can also see if there's a very serious issue that's really close to failure. That's where an online PD can give you some useful information. But again, that might be too late because the system's already in jeopardy at that point. So by comparison, Synaptics' approach with Greenlight here is that we can find a broader set of failure modes. So not just insulation issues, which is primarily what PD is telling you about. And also we focus on the joints and terminations. And so we've hopefully given you an idea about our sensors are practical to deploy. And once they're deployed, they don't need any maintenance as well. So they're designed to last as long as the primary asset itself. So nobody needs to visit that sensor location and change a battery or anything like that. It's all self-sufficient once it's deployed. So that's where we fit in. We see ourselves as being complementary to PD monitoring and offline testing approaches. But ultimately, once the system is online and the asset's working 24/7, we provide the kind of intel on what's happening and the opportunity to find things at an early stage that isn't really possible otherwise. So I think at this point, I'll hand back to Saul to talk about the return on investment part here.
Yeah, so very often in these webinars, we get justifiably excited about how cool our technology is and the fact that we can see all these amazing parameters as if they were right next door to us inside the substation, even though they're very far away underground or underwater. One of the things that we always try and keep ourselves honest about is, well, what does this mean in practical terms to the owner or operator of the asset? And I wanted to use this slide as a kind of a directional indicator of how we try and approach these problems. I won't go into the super detail of all the numbers that are involved, but the concept here is to say, when we work with a customer, could be a grid operator or an offshore transmission operator, or indeed a generator of power in the renewable sphere. Yes, we talk about the idea that there is a fundamental risk of failure here. It just so happens that the most dramatic failure events and some of the highest costs are in the public domain because they're reported by the way that offshore wind farms are regulated, so we can see their data. But very often you're talking over a 30-year operating period. You might expect a certain frequency of failure events. And when you run calculations based on real-world reported failures that have been documented, you can start to come up with a language that says look, you've probably got several $100 million or pounds worth of risk. And of course, we're trying to propose a system which is, by comparison to either that risk or to the cable budget itself, a de minimis amount, a very small amount of money, a single-digit percentage amount to mitigate a significant risk in the future. But of course, dodging these bullets or avoiding these failure issues is not the only thing that Greenlight is doing, because some people can argue that failures didn't happen to me or haven't happened to me yet, or they're very far in the future and not sure or certain. So we accept that and we understand that. But that's not the only thing that Greenlight is evaluated by. The other thing is to talk about these sort of day-to-day ongoing operational cost savings, which might sound modest by comparison to avoiding a $50 million outage, but they're quantifiable. And the quantification comes from having increased availability because you're undertaking fewer visits and manual inspections, and you've got better targeted and data-driven interventions when you do go and maintain and visit, or you're using that information to improve the duration of planned and scheduled outages because you're better informed going into them. Or having just done the testing, you've got data that then immediately shows deviation against that fingerprint of data. So that's a very powerful tool in terms of day-to-day operational costs. And when we talk about yield, this idea of pushing a cable a little bit harder at a certain peak demand time or peak production time, well, yes, clearly we want to be able to maximize that capacity, but completely safely with no downstream lingering effects or damage being incurred onto the asset. So you're able to see a language here where we're talking about fewer visits, engineers retasked to do other much more useful things. There are some hidden cost benefits as well, like in the subsea domain, you need to do fewer subsea ROV inspections, which are horrifically expensive. If you can avoid sending out massive SAV or service vehicles instead of crew transfer vessels, then you're spending thousands instead of millions of dollars in vessel costs and diesel costs. And if you can simply avoid some of the failures and reduce some of the scheduled inspection visits and automate that, you'll see significant return on investment. 20, 30-fold is entirely possible over the lifetime of this device. And as Stephen said, when you install Greenlight, one of the benefits of passive sensing is you can fit and legitimately forget those sensors. There are no active electronics. There is no capacitor or battery on board. They don't have those risks or failure modes. You're not replacing a human visit with a device that then needs visiting and inspection, so you haven't saved any money. The idea is to install these things, and when we've done our own lab testing, where we do accelerated life testing of these sensors, we've taken them past 140, that's 140 years, before they lose any accuracy. So this really is fit and forget. You put these sensors out there in these places which are remote and inaccessible, and they will simply continue to operate way past the scheduled operational life of the primary asset. Now, one of the other soft benefits that we don't even list here, health and safety. Certainly for the cables that we monitor today in OSI, and as most people know, they are incredibly dangerous and volatile tubes. And if you can improve safety by not exposing your workers, kind of monitoring this asset in the most green and power unintensive way possible, that's goodness. And these are all become like a catalog of scores that we can build up to help with the business case justification. But if we were to summarize all of that, what we're trying to convey today is the idea that you have a fundamentally low touch, small footprint, and very scalable real-time monitoring solution that can reach all of these locations and provide very simple, empirical, and therefore actionable information to help you take critical decisions about taking an asset offline, repairing or re-terminating critical elements within the cable system. Or perhaps you're looking at the very long term and saying, towards the middle or the end of the operating life, how is this thing actually degrading over time? Can I avoid decommissioning, and can I repower and keep going with this asset and literally sweat this asset and make it last longer whilst maintaining high levels of availability and reliability in the field? So you can only do that if you build a history of data that shows you for all of these locations what's happening and where you've got exceptions and excursions and deviations. So if you remember back on one of those slides, we showed you how in that cable system, we were monitoring 20-something locations, but only one of them was problematic. So the message here is, well, just come and visit this one because this is the one that needs the attention. The others, you don't need to go and check. They're okay. We've done that work. You can stop worrying about them and focus your energy and your attention to where it matters. So if you can apply that kind of data-driven asset monitoring and maintenance methodology, and you can integrate permanently and synchronously all of these parameters. So the electrical stresses, the mechanical stresses, the thermal stresses, bring them all into one picture. You get a much higher confidence source of information that we can publish and then provide to you. And then you can use that data to make some, again, more informed decisions. And we're not saying that you should use this on its own instead of any other methodology. Very often our customers will say, no, please give me your technology and incorporate it with things like distributed temperature sensing or scheduled testing using much bigger offline testing equipment that's provided by Mega. What we're saying is it's best to do both, because then over time you build that data history and you have more and more information to base your decisions on. And what we often find is a customer will ask us not only to provide the hardware system, but also to provide that data online through SCADA so that they can access the data using like a REST API to validate things that we've signposted and said, here's a problem. But we are looking offline in the cloud at these trends and advising the customer can refer to that and say, yes, I think you're right, but I'll still validate it. And I'll have a look at my other SCADA feeds and my other sensing technologies and try and get that confidence that yes, it really will be worthy of taking offline, and we do need to intervene to fix something. So overall, the concept of Greenlight here is to try and radically reduce the amount of manual and periodic scheduled inspection that happens, because that improves operational cost and it improves safety. It's about optimizing that scheduled maintenance by focusing on where we've got problems and not worrying about places that are actually fine, so that you focus on managing exceptions, not the rule. And it's about optimizing utilization, because hopefully what we were able to show you there is we're catching these critical thermal bottlenecks that could easily be overlooked when you're trying to do dynamic rating and make the system more flexible and more responsive. And overall, of course, this is about maximizing availability and uptime, because we're able to give confidence about spending money on interventions. Now, we realize that's quite a big set of claims, but the point of this webinar is to help you appreciate that there is a technology out there which is able to be installed new or retrofitted quite readily. It's also very fast and safe to install, and also incredibly easy to commission, because you do that centrally. You don't commission every sensor at every location, so it's quite rapid. And when you've got that data, either you as the customer can take that data and integrate it into your own asset performance management systems or SCADA to decide how to interpret. But as Stephen mentioned, you might not want this fire hose of data coming at you, and you might need help. And we provide that service too. We can interpret that data and tell you when we think there's a problem. And most of the things that are captured here, these interesting correlations and exceptions, Stephen's team has designed the Greenlight system to automate the signposting of these problems. So we're really trying to take away uncertainty and make it as deterministic and actionable as possible. When you combine that with all of the other best practice testing methodologies, it's for sure going to fundamentally de-risk using power cables, which these days is simply inevitable for all kinds of reasons. So we hope that that has made the concept of Greenlight clear to you. We can see from the Q&A that it's generating a lot of questions, and there are a lot of specific case studies. So I'm sorry if we're failing to keep up with the questions here in real time. There are rather too many to keep answering, but I hope that what we've managed to do here is give you the overview needed to make you realize it's possible to have more visibility and control of these assets for a price that's a proportionate to the value you get by avoiding problems and wasting money on unnecessary interventions and inspections and visits. And if you are curious about that idea, our request is to get in touch. There are some links here, and there are also some email addresses that have been provided to you in your registration, so that you can contact your local sales rep, who will bring our team in as an expert witness to take you through specific examples of how it might apply to you, because unfortunately we're trying to give a very general overview here, but of course everyone's got very specific topologies, voltage levels, applications, and uses of underground and subsea cables. So apologies if we didn't manage to address everything for you. Now, that said, I've noticed we've got a few minutes left here, and if there's a single common set of questions that we can quickly answer with the time remaining here, Stephen, there might be one which could be to explain to people how we manage data and then provide the analytics services. So how much is online and automated versus how much the data needs to be exported into the cloud so someone else can interpret it. Could you give people a quick sense of that with the few minutes that we've got remaining, please?
Yeah, sure. So the system is designed to be fully standalone and run 24/7. So the sensors are obviously distributed over distance in remote locations, but the fiber brings that back to a central location. Typically it's going to be a substation, could be an offshore substation, or it could just be a regular substation in the grid. In a substation somewhere, there'll be a rack where we have our interrogation systems. So that does the conversion from the optical signals into actual data, to time series data effectively. And then we have what we call our synthesis server, which does further processing of that data into more useful quantities, like, here's the RMS, here's the phase measurement. And then it does another layer of processing, which is looking for anomalies in the data. And that's how we really extract the value from this. So being able to see far and wide and compare different locations and different sensor types over time and over distance is kind of how we derive value. There is an option that we have available where this could be linked with a secure cloud service. So essentially that provides full backup of the data. Effectively, you're no longer limited to the local storage within the server. Also, if something catastrophic was to go wrong, then there would be a backup of the data in the cloud. That also allows us to analyze the data and provide reports, regular reporting to the operator. So we can learn things and the operator can learn about what's going on in their system. And we use that to actually improve the Greenlight product itself, to give it better, to refine its capabilities, allow it to detect ever more subtle events that could lead to genuine failures in the future. Yeah, so I think that covers the overall architecture.
I think so. I think that's a really important point, because very often we've managed to design the system to take care of differing policies and attitudes to data security and sort of IT policies. Sometimes the customer wants us simply to create data on site, inside of the firewall, inside of the substation, generate data that then they can go and interpret. At the same time, the same technology and the same platform is able to not only store and buffer and serve up data there for someone else to consume and interpret, but we can automate those correlations and give insights and actionable responses to it. And finally, other customers have also asked us to stage that data in the cloud and have a longer term view of it, so that we can write, for example, monthly or quarterly reports to give interpretations of where we think we can see problems brewing. But again, the critical thing is to try and identify as early as possible something that's anomalous that requires focus. It might not be catastrophically bad yet, but that's good. We're trying to anticipate these problems and give you time to do something about it before it does become a significant event and creates an outage and costs too much money to fix. So we hope that all makes sense. And we're also very conscious that now we're at the top of the hour and we've pretty much used our time up for today. Again, apologies if we haven't answered all of the questions live that were posed. I promise we'll keep a note of them and get back to you. We've been feverishly trying to type and scribble down information to make sure that we can follow up with you. And again, to remind everybody, this will be made available as a recording and a link emailed to you all tomorrow. But most importantly, I just wanted to stop and say, first, thank you to our team here and to the Mega team for hosting this event. Thank you to Stephen for taking us through the detail of all this. But most importantly, thank you to so many of you who have joined us today and given us your time. We hope that's provoked your interest and your thinking, and we invite you to come and engage with us so that we can tell you how this applies to you and your business in much more detail very soon. So with that, thank you all very much for your time, and we look forward to talking further with each of you about your specific requirements. So thank you, and have a great afternoon, evening, or morning, wherever you are in the world.
Great. Thanks.